Assalamu alaikum everyone. Today we are going to start A2970142 February March 2025. So it's A2 chemistry paper 4. Okay. So question number 1. Silver Ag is a metal in the D block of the periodic table. Okay. Silver can form compounds containing either Ag positive or Ag2 positive ions. Explain why silver is a transition element. So, if you recall the conditions to be a transition element, the one which has incomplete D subshell and that incomplete D subshell when it exists as an ion. So, you can write that silver is transition as it has incomplete D subshell when it form ion. So it's one of the ion has a incomplete D subshell, and that's why silver is considered as a transition element. Now, part B, table 1.1 gives data relevant to the Born-Haber cycle for silver 1 fluoride. So see, it's silver 1, which means silver plus 1 ion and fluoride 1 minus ion. Okay. The first ionization energy is given for silver. That is enthalpy change of atomization of silver. Then enthalpy change of atomization of fluorine. Then enthalpy change of formation of silver fluoride. And then the lattice energy of silver fluoride. Okay. Write equation for these standard enthalpy changes described include state symbols. So see, they have mentioned state symbols, so you don't skip those. And remember, read the question very carefully. So enthalpy change of atomization of silver. So if you recall, the enthalpy change of atomization is always when an element turns into atoms in the gaseous state, and the element can be in any state. So it's for silver, and we know silver is a transition element, right? So if it's a transition element, so it is going to be a metal and it's a solid. So silver solid and then arrow, and 1 mole of gaseous atoms would be formed. So Ag with the gaseous state. Then standard enthalpy change of formation of silver 1 fluoride. So for formation, if you recall, the equation has elements in the reactant form side and 1 mole compound on the product side. So that is the enthalpy change of formation. So over here, we are going to use the silver, which is a metal again. Then fluorine. Remember, fluorine is a diatomic gas. So you have to put F2 and then gas and then fluoride. So silver fluoride has a formula AgF, and it's an ionic compound, so it is going to be solid. Okay, so we are going to balance the equation in such a way that the silver fluoride that is formed stays 1 mole. So I'm going to put a half over here to balance the equation. Now, as a result, we will have a 1 mole of silver and 1 mole of fluorine, or half mole of fluorine. Clear to all of you? Okay. Now, next part. Here they are asking for the definition lattice energy. So You can write that it's an enthalpy change. It is an enthalpy change when one mole and ionic compound is formed from the gaseous ions, or you can write from the constituent gaseous ions. Yeah, you can write it the energy released when one mole of uh, ionic compound or ionic solid is formed from gaseous ions under standard conditions. I hope it's clear, and I hope that everyone remember the uh, definition. So now next part. Calculate the first electron affinity of fluorine using the data from table 1.1. It may be helpful to draw labeled energy cycle as a part of your answer. Okay, so we can make the label energy cycle, and it will be very, uh, easy if you make the Hess cycle and then you make the mathematical expression from it, and so you can easily solve it. So what they are asking you to calculate the first electron affinity of fluorine, right? So, for example, what we know that when I have a Ag positive ion in the gaseous state and I have a fluoride ion in the gaseous state, and they are turning into silver fluoride, right? So this equation, the enthalpy change of this equation is represented by lattice energy. Now, what I can take, as they are talking to calculate the electron affinity, right? So what I'm going to take the elements over here, and we need 1 mole of a silver and half mole of a fluorine gas, right? And when silver and as an element and fluorine as a element joins to form, reacts to form silver fluoride, the enthalpy change of this is considered as enthalpy change of formation, right? And then the silver ion and the silver and the fluorine both can be turned into uh, gaseous ions. So if we look at this side, the left side, so silver is turning into a silver ion, which means that, and it's a silver solid, which is turning into gaseous ion. So it means over here, we need the enthalpy change of atomization of silver. And then we need the first ionization energy of silver. And then fluorine from the molecule turns into atom and then gaseous atom and then into ion. So we need the atomization of fluorine, and then as it turns into a negative ion, so we need a first electron affinity of fluorine. So till here, is this understandable to all of you? Now, if you see, this is where the cycle starts, right? And this is the point where the cycle ends. So if you see this turn into ions and then turn into this, so this is your indirect route and this is your direct route, right? So from this, I can easily make the mathematical equation, and that mathematical equation is that the enthalpy change of formation is equals to enthalpy change of atomization of silver, first ionization energy of silver, plus enthalpy atomization of fluorine, then first electron affinity of fluorine, and then the lattice energy. So this is what examiner asks you to calculate, right? So I'm going to make it a subject. So it is going to be first electron affinity of fluorine is equals to, I am going to keep it this side and move the all of the other to the opposite side, is equals to enthalpy change of formation minus enthalpy change of atomization of silver, right? Okay, so, and all the things are going to be negative. So minus first ionization energy of silver minus enthalpy change of atomization of fluorine and minus lattice energy. Till here, this expression, the Hess cycle, is it clear to all of you? If any one of you has any confusion in this, please ask. Okay. So now we are going to take the expression values and see, we are getting 1 moles. So no need to multiply any of the value with the 2 or 3 because everything is 1 mole. Okay. So we have what we need. We need the formation. So the formation is this minus 203. Then we need atomization of silver. So atomization of silver is, so that is positive and the sign is negative. So positive, negative makes it negative. So my negative 289. Then first ionization energy of silver. So the first ionization of silver is positive 730. So over here, negative first ionization energy of silver. So positive, negative makes it negative. So minus 732, then negative atomization of fluorine, and the atomization of fluorine is 79. So positive, negative again makes it negative, and then the lattice energy. So lattice energy is minus 955, and it is negative. So negative, negative makes it positive. So positive 955. Okay. So can anyone solve it and tell me the answer? Okay, Faizan. Thank you, Faizan. Thank you, Rohan. So the answer we are getting is minus 348. And over here, the unit is already mentioned. If the unit is not there, then you need to mention kilojoule per mole. Okay, so minus 348. Okay, yeah, minus 348. So minus 348 kilojoules per mole. I hope it's clear to all of you. Now, next part. If any one of you has any confusion till here, please do ask. Use the data in table 1.2. Okay, here it is. Calculate the enthalpy change of solution of silver fluoride. Okay, so if you recall, it's a silver fluoride. What is given? You are provided with the lattice energy. You are provided with the enthalpy change of hydration of silver, and you are provided with the hydration of fluoride. So if I again make the Hess cycle, keeping in mind these three, so silver ion in the gaseous form, reacting with the fluoride ion in the gaseous form, forming silver fluoride solid, and that is the lattice energy, right? Then I have elements, silver, 1 mole, and half mole of fluorine. These elements turning into a compound that is enthalpy change of, okay, no, 1 minute. Sorry. Yes, we are going to use this expression, Shahir. So if you don't remember the expression, see, as they have given you the solution, or so what you are going to do, you are going to take the ions in the aqueous state over here. So when the silver fluoride dissolves to give the aqueous solution, that is the enthalpy change of solution of silver fluoride. And when these ions, so each ion individually dissolve from its gaseous state to the aqueous state to the solution. So over here, this is this enthalpy change of hydration of silver ion plus enthalpy change of hydration of fluoride ion. And again, if you see, these all are 1 mole. So uh, we are not going to multiply any of the values with any other number. We are going to take the values. Now, if you see the expression, the Hess cycle, so this is the point where the cycle is being started. That is the starting point. And both the arrows are pointing towards these aqueous ions. So this is the point where the cycle is being ended, right? So if you see, this is your direct route and this is your indirect route, because these gaseous ions first turning into a solid and then it dissolves. So from this, I can make the mathematical expression initially that enthalpy change of hydration of silver plus enthalpy change of hydration of fluoride ion and silver ion is equals to lattice energy plus enthalpy change of solution. And if you see, they ask you to calculate the enthalpy change of solution. So I need to calculate this one. So I'm going to make it a subject. So if I make it this subject, so it is going to be enthalpy change of solution is equals to enthalpy change of hydration of silver ions plus enthalpy change of hydration of fluoride ions minus lattice energy. So the enthalpy change of hydration of silver ion is minus 464 and then plus, and it is also minus, so plus minus makes it minus, so minus 506 and then minus, and the lattice energy is negative, so negative negative makes it positive, so positive 955. Can anyone solve it and tell me the answer? Okay, so what we are getting, minus 15 kilojoule per mole. So it is going to be minus 15 kilojoule per mole. Is this clear to all of you? Okay. Now, next part. 2. Use your answer to C1 to suggest whether the silver fluoride is soluble in water at 298 Kelvin. Explain your answer. Yes. Who remembers this? Not soluble. Shazil is saying not soluble. Yes, Faizan, very good. Yes, it is soluble. Remember, enthalpy change of solution is negative. This it is soluble. Okay. So you must remember that enthalpy change of solution, if it's positive, then the compound is less soluble. And if it's negative, then it is more soluble. So we are going to write that it is soluble as its enthalpy change of solution is negative. And further, you can write if you it is because you can take this expression that if you see you are getting this negative, right? So if it is negative, then it means these hydrations are greater than the lattice energy. So enthalpy change of hydration is more exothermic than the lattice energy. This makes the enthalpy change of solution negative, and the compound becomes more soluble. Yes, very good, Faizan. It is because the enthalpy change of hydration is more exothermic or more negative than the lattice energy. That is the reason. Now, D. Table 1.3 shows some data to the silver 1 halide, silver chloride to silver iodide. Okay. So these are the electron affinity trends as we have discussed, if you guys remember. So if you see the periodic table, we have a fluorine, chlorine, bromine, and iodine. So they have used the silver compounds of chloride, bromide, and iodide. And if you see over here, they have given you the first electron affinities of the halogens and then their lattice energies. Okay. So what they are asking, explain the trend in first electron affinities of the halogens from chloride to iodide. So what we are observing, what is the trend? The trend is they are being getting less exothermic, right? Yes, the electron affinity values decreases. Very good. Shazil, very good, Faizan. Shahid, you are not going to use the term atomic radius because these are not atoms and these are the compound. So, yeah, ionic radius. So, electron affinity values getting less exothermic because the ionic, and it's for 2 marks, right? Radius increases. And why the ionic radius increases? Yes, number of shells, very good, Shazil. So it means there is an increased shielding effect. Ionic radius increases, shielding increases, right? Hence, nuclear attraction gets weaker. No, it is the both things are going to affect the nuclear attraction due to not only just the sizes being increased, the shielding effect. There are more electron shells, so there are more electrons which are shielding. So as a result, the nuclear attraction gets weaker for the incoming electron because the electron affinity is associated with the gain of electron, isn't it? So the incoming electron. I hope till here it's clear to all of you. If anyone of you has any confusion till here, please ask. Okay. Now, explain the trend in lattice energies of silver 1 halides. So if you see, they are also getting less exothermic. The lattice energy values. So the same reason that uh, ionic radius of the halide ion increases from chloride to bromide to iodide. So the charge density decreases and the attraction between the silver ion and the halide ion gets weaker. So it becomes less exothermic. So the lattice energy values gets less exothermic from silver chloride to silver bromide to silver iodide due to increase in ionic radius of halide ion, which leads to weaker, and between the ions there are electrostatic forces of attraction. So weaker electrostatic attraction between silver ion and halide ion. Okay. Now part E. An electrochemical cell is constructed using electrodes shown in table 1.4. Calculate the standard cell potential E0 cell, construct an equation for the overall cell reaction. Okay, so calculate the E0 cell. If you recall, E0 cell is equals to E reduction minus P oxidation. So the one with the greater value undergo reduction. So it will this one undergo reduction, this one undergo oxidation. And remember, the flow of electron is always from the electrode where the oxidation occurred towards the electron where reduction occurred. So, and the one where the oxidation occur, you have to flip that equation as well. So you are going to mark all these before attempting. So it is going to be 0.342 minus 0.222. Okay, thank you, Faizan. So the value is 0.120 volt. So I'm going to write 0.120 volt. Okay. Now for the equation. The equation for the copper is going to be the same as it was in the table. But I'm going to flip the equation for the silver. That silver ions plus chloride ions. Silver chloride plus electron. And I'm going to make this equation multiply by 2 to balance the electrons. Now, the electrons are going to be cancelled. Now we have Cu2 positive ions reacting with 2 Ag positive plus 2 Cl negative, forming Cu plus 2 silver chloride. And remember, in this equation, don't use the reversible sign. In this equation, when you make the net equation, in the net equation, there is always a forward sign, because from the E naught cell, as we are getting positive, which indicates that the positive reaction occur, its backward reaction doesn't occur. Yes, it's Ag. It's not Ag positive, my bad. It's Ag. So Cu2 positive, 2 Ag, 2 chloride ions forming copper and 2 moles of silver chloride. Okay, I hope it's clear till here. Okay, now next part. In different experiment, electrode 1 is set up using a saturated solution of potassium chloride. Saturated solution of potassium chloride contains 36 gram of potassium chloride per 100 centimeter cube at 298 Kelvin. The next equation of electrode 1 is, okay. So see what they are doing. Instead of this electrode 1, now this is the electrode 1 using potassium chloride. Okay. Now, here you got the equation. In this equation, this is the E naught, that is the standard value that is being provided. Z is number of electrons in half cell. Right? And we need the concentration of chloride. Okay. So first we need to calculate the concentration of chloride, and we have this value. So first what we are going to do, we are going to convert the mass into moles of potassium chloride. So moles of potassium chloride is equals to 36 divided by the MR of potassium chloride. So potassium is 39.1 and chloride is 35.5. Can anyone add the values? 39.1 and 35.5. Yes. So it is going to be 74.6. And when you divide these two values, the moles you will get are 0.483 moles. Thank you, Faizan. And thank you, Rohan. Okay. So we have calculated the moles. So these moles are present in 100 centimeter cube, isn't it? So we can use the formula to calculate the concentration. Okay. One more thing. We need the concentration of chloride ion, and the compound contains 1 mole of potassium ion and 1 mole of chloride ion. So the concentration of chloride ion is going to be same as the concentration of potassium chloride. And calculate the concentration, we are going to divide the moles with the number of with the volume. So moles are 0.483, and the volume is 100 centimeter cube. So we divide it with the decimeter cube 1000 to convert into dm cube. So it is going to be 0.1. So yes, can anyone calculate the concentration, please? So it is going to be 4.83 mole. Thank you, Fazan and Shazil and okay, mole per dm cube. So these are the concentration of chloride. Okay. So if you see this equation, so actually what happens that instead of this, now we have this equation that potassium chloride solid gaining 1 mole of electron, forming potassium and the chloride aqueous. So see, in this case, only we have a chloride ion in the aqueous, so the electrode potential is 0.22. So if instead of silver ion, if we have any other metal, but we have only getting a chloride ion, so E naught value is going to be the same, positive 0.222 volt. Is this understandable to all of you? So see, if this is the case, then value of Z is equals to 1 as well. Now we are going to put the values to calculate the E value, the electrode potential under non-standard conditions. So E naught is going to be 0.222 plus 0.059 over 1 into log to the base 10 times 1 over concentration of chloride ion, which is 4.83. So thank you, Rohan and Faizan. If we calculate it, it is going to be 0.182 volts. So the value is 0.182 volt. Till here, is this clear to all of you? Okay. Now, question number 2. So propane, CH3, COCH3 is a common organic solvent and reagent. Propanol, my bad. Sorry, propanol. So propanol reacts with the methanol, CH3OH, under acidic conditions to form a compound A shown by reaction 1. So if you see in the equation over here, the H positive is over the arrow. So that acidic conditions, it refers to the acidic conditions. And further, it refers that it is used as a catalyst because it is on the top of the arrow. Okay. Now, the overall order of a reaction one can found by studying experimental data. Okay. So table 2.1 shows the initial rates of reaction changes as the concentration of methanol and hydrogen ion are varied. In each experiment, a large excess of propanol is used. Okay. So it is in large excess and the concentration of methanol and hydrogen is being changed and their effect has been studied on the rate, right? Okay. So here we have these values. Explain why a large excess of propanol is used in each experiment. Yes, very good, Shazil. Because if it's in a large excess, so if it reacts, there is the change or the concentration of propanol that has been used up is actually not significant. Its change is it's the amount of the propanol as it's being used is not significant. So as a result, its order becomes 0. So there is negligible change in concentration of CH3 COCH3. Hence, its order become zero, and the effect of changing concentration of hydrogen ions and the concentration of ethanol can be studied. So we are going to study or examine the effect of the changing the concentration of both the other two reactants, and there is no effect on the rate due to the change in the concentration of propanol. I hope it's clear to all of you. Now, use the data in table 2.1 to determine the order of reaction 1 with respect to methanol and hydrogen ion. Explain your answer. Okay. So, see, these two are constants, and by some factor, the concentration of hydrogen ion is increased, right? So we have to identify the factor by which the rate is increased and by the which the concentration of hydrogen is increased. So for hydrogen ions, use experiment 1, sorry, experiment 2 and experiment 3. The concentration of hydrogen ion, can anyone tell me by which factor the concentration is increased? From 50.015 to 0.20, it's the factor of 1.33. Okay. So the concentration of hydrogen ion is raised, and with the same factor is the concentration, is the rate is also increased. So the hydrogen ions, the concentration of hydrogen ion is raised by the factor of 1.33, and rate is also increased by same factor. Hence, order with respect to hydrogen ions concentration is first. Is this clear to all of you? No, it's not possible that it's zero. If I divide 0.20 divided by 0.015, 0.020 divided by 0.015, it's 1.33, and 3.00 divided by 2.25. 3.00 divided by 2.25. Yes, 1.33. So it's a first order. It's not. Okay. Now, what I can do now, you can go for experiment 1 and 2. By which factor this is increased? Can anyone tell me? Okay, Shahid. So we have to show the working as well. It is increased by the factor of 1.5. If you see, This is also increased by the factor of 1.5. And by which factor it is increased? It is increased by the factor of 2.25, right? So see, 2.25 is the square of 1.5, right? So see, 1.5, the rate is increased by the 1.5 due to the increase in 1.5 times concentration of methanol, and rate is also increased by further 1.5 due to the increase in the concentration of hydrogen ion by 1.5. So it indicates that the concentration of methanol is also has a first order. Yeah, so both has a first order. So I'm going to write that from, so we are going to use experiment 1 and experiment 2. So from experiment 1 and experiment 2, the rate is raised by 1.5 times due to increase in concentration of methanol by 1.5x. Rate is further raised by 1.5 times due to increase in concentration of hydrogen ion by 1.5 times. Hence, order with respect to methanol is first. Is this clear to all of you? Yes, if you can show it mathematically, both the things, then it is fine as well. And if you can write, examiner can accept both the ways, okay? So you can, if you can represent this whole thing from experiment 2 and 3 for hydrogen and for methanol from experiment 1 and 5, mathematically, then it is fine as well. Okay. Now, in a separate experiment, a large excess of methanol and hydrogen ions are added to the solution containing a known concentration of propanol. So see, in this experiment, these two are in the large excess. So it means these two are going to have a zero order, right? Figure 2.2 shows how the methanol concentration varies over time. Okay. Use figure 2.2 to show how under these conditions reaction 1 is first order with respect to concentration of methanol. So what you are going to do, you are going to calculate the half-life. If the half-lives are constant, then you will get that it's first order. So initially it's 100, right? So the half is going to be 50. So you see the first half-life. Then half of the 50 is 25. So if you see the half-lives, so if you see the first half-life, it start from 0 and end over here. And if you see the second half-life, So the first half-life is 170 and the second half-life is 340 minus 170 is again 170, right? So for a first order, the half-lives must be constant, and we are getting the first two. So the two successive half-lives are constant, that is 170 seconds. Is this clear to all of you? No, it's 340. See? 310, 320. Yeah, okay. So 330, which makes it 160. So over here, you are going to write around 170 seconds. Yes. No, it's not necessary that it is going to be exactly the same. It is plus minus 5 or 10 seconds that are all accepted. If the half-lives are not constant, then there is a significant difference in them. For example, if I go for the third one, so third one is going to be 12.5, right? So if you see 12.5 is around this. If you have a doubt, you can check the third one. So from so what is the third case? It's around 500 minus 330. So again, you are getting 170, right? So these are almost the same. So that's why it's first order. Okay, now. Okay, now B part. Propanol also reacts with the acidified cyanide ions to form hydroxyl nitrile compound B as shown in reaction 2. So if you recall, that is what you have studied in. Okay, that is not that is hydrogen cyanide, not acidified cyanide, but this kind of a reaction is in AS. Now, the following rate equation is determined for reaction 2. Okay. So four possible mechanisms for reaction 2 are shown in the table. Okay. So as these two are here, so these two must be present in slowest step and 1 mole of each, right? 1 mole of each must be present in the slowest step. So if you see these two are in the fast step, so it is wrong. Hydrogen ion is in the fast step, so it is wrong. Cyanide ion is in the slowest step and cyanide ion is not there, so it is wrong. Over here, see, these two are in the slowest step, so yeah, experiment. So the proposed reaction mechanism is going to be the mechanism 4. Is this clear to all of you? So it is consistent with rate equation as in slowest step, no cyanide ions are present. Slowest step involves 1 mole of each hydrogen ion and propanol. Is this clear to all of you? Okay. Okay, now C part. Carboxylic acid C4H8O3 forms when B is hydrolyzed under hot acidic condition. Draw the structure of C. So if you see that is B, if you hydrolyze it, so this cyanide is turned into carboxylic acid. This is going to undergo hydrolysis. So we have CH3 bonded to C, and there is another CH3 bonded to it. There is a OH bonded to it, and there is a CN. So that CN is actually turned into a carboxylic acid. Now, if you see, you have 1, 2, 3, 4 hydrogens, 3 oxygens, sorry, 4 carbons, 3 oxygens, and 8 hydrogens, right? Now, the pK of C is 39.95. Okay. Calculate the pH of 0.5 mole per dm cube solution of C. Show your working. Okay. So from pK, we can calculate the Ka. Ka is equals to 10 raised to the power minus pK. That is the expression. So Ka is going to equals to 10 minus 3.95. Can anyone tell me the answer? Yes, Faizan, very good. Yes, it is going to be the, so that we got the K value, which is 1.22, sorry, 1.122 exponent minus 4. Okay. Now, hydrogen ions can be calculated for a weak acid by this expression. Hydrogen ion is equals to under root Ka times concentration of acid, right? So 1.122 times concentration of acid is 0.500. Yes. Can anyone tell me the concentration of hydrogen ions? 7.49 exponent minus 3. Sorry, minus 3. Now we are going to calculate the pH, which is equals to minus log 10 concentration of hydrogen ions. So pH is equals to minus log 10 of 7.49 exponent minus 3. So the pH we get is 2.13. Is this clear to all of you? You just give me a minute. Okay. Now, next part. No, it's it weak doesn't mean that it's 5 to 6 pH. pH 2 or 3 are also considered as a weak. Okay. C can be used to form buffer solution D, define a buffer solution. So its definition, I hope you all remember, a solution which resists the change in pH when a small amount of acid or alkali added to it. Okay. Now, next part. Buffer solution D is made when 20 centimeter cube of 1 mole per dm cube NaOH is added to 100 centimeter cube of 0.5 mole per dm cube solution C. The pKa of C is 3.95. Calculate the pH of buffer solution D. So first thing, if you see, the total volume of buffer is mixing 20 centimeter cube and 100 centimeter cube is going to be 120 centimeter cube. Okay. Now, so C has a 1 carboxylic acid. So it is going to react with the 1 mole of NaOH, right? So you can just make the equation that C plus NaOH gives you salt and water. We are going to make the ice table to find the concentrations of each at equilibrium, and then we are going to use the pH expression for buffer. But for that, we have to calculate the moles. Okay. So the moles of NaOH is equals to 20 times 1.00 over 1000. So it is going to be 0.02 moles. The moles of C is going to be 0.5 times 100 over 1000. So it is going to be 0.05, right? Okay. So we got the moles. So the moles of C are 0.05. The moles of NaOH are 0.02. They both react in the ratio of 1:1. So it means the NaOH has a lesser mole, so it is going to be used up whole. And the C is going to be just used up 0.05. So at the end or at the equilibrium, when the equilibrium has been established, we had 0.03 moles of C, that is a weak acid. We have 0 moles of NaOH. And initially, we don't have any of these, but the mole ratio is 1:1. So we got the salt, we got the acid both. So over here, the buffer solution is ready because it has an acid and it's salt both, right? Okay, Shazil 1.63. Let's see. I don't know. We are just doing it. So pH is equals to pKa, that is the expression for the buffer solution, plus log 10, log to the base 10 of the concentration of salt over concentration of acid. So now what you need to do, you need to put the values. pK is 3.95 plus log 10. Okay. So as we are going to take the one concentration above and one concentration below, and these are the moles. So I'm going to use the moles directly because to find the concentration, I have to do this. For example, this 25 over 1000 and 25 over 1000. So this is going to be cancelled out. So we can directly use the moles. It's 120. So 120 over 1000, but it is going to be cancelled out. So over here, the concentration of it is going to be 0.02 over 0.03. Yes. Okay. Yes, Shazil, you are getting the answer which you have told me is with the same thing. Okay, Shahir and Faizan, you are telling me the answer is 3.77. Okay. Thank you, Shahir, Faizan, and Rohan. So the answer is 3.77. So the pH would be 3.77. Yes, Shazil, is it clear to you? Okay. So is it clear to it's clear to all of you? If any one of you has any confusion, any question, please ask. Okay. So I'm keeping the session till here for today. And we are going to continue this paper tomorrow. And inshallah, tomorrow we are going to because okay, it's organic, so it takes lesser time. And how many questions we have? We have 6 questions. Okay. So we will continue from here onwards tomorrow. Which one, Arish? See, the buffer is a combination of a weak acid and its conjugate base or weak acid with its salt, right? So see, we have calculated the moles, that is a strong base, and this is the weak acid, right? So when weak acid reacts with the base, the salt formed is a conjugate base, isn't it? Is this understandable, Arish? And everyone else, if anyone else doesn't understood, I'm explaining. So see, we calculated the mole. So see, the reacting ratio of both of them is going to be 1:1. So as there are lesser moles of NaOH, so NaOH is going to be used up completely, and the mole ratio is 1:1. So equal moles of NaOH and acid are going to be used up. Is this clear? So if these moles are of NaOH is going to be used up, and these are the initial moles, so at the end there is no strong base left over because all of the strong base have been reacted. Is this clear? But we got this much amount of acid left over. That 0.03 moles of weak acid is still uh, doesn't react, it left unreacted, right? And now the ratio of the base with the salt is also 1:1. So the moles of as base which has been used up, the equal moles of the salt has been produced, right? So now when the equilibrium has been established, we got the weak acid and its conjugate base or its salt. So it's a buffer now. So now we use the expression for the pH of a buffer. We put the values and get the pH. Is this clear? Okay. So we are ending the class here, and from here onwards, for 3, we are going to start tomorrow, same time from 9. And tomorrow, we are going to complete the whole chapter. We have 4 questions left, so we will do those 4 questions tomorrow. Okay. So see you everyone tomorrow. Take care. Goodbye and Allah Hafiz.